Hello guys, welcome back to my channel. This is G Varun, pursuing my education in Sri Venkateswara College of Engineering, Bengaluru. Today in this video, we will discuss about curve fitting by the methods of least squares. Introduction to curve fittings by the methods of least squares. Curve fitting is a mathematical technique used to find the best fitting curves that represents a set of data points. The method of least squares is a popular approach to curve fitting that minimizes the sum of the square deviations between the data points and the fitted curve. Curve fitting by the method of least squares is widely used in various fields, including statistics, physics, engineering, and finance. Understanding the least square methods. The least square methods aim to find the curve parameters that minimizes the sum of the square differences between the observed data and the predicted values by the fitted curve. The method assumes that the errors between the observed data and the fitted curve are normally distributed and have constant variance. By minimizing the sum of the squared errors, the least squares method provides an optimal solution for curve fitting. Steps for curve fittings by the method of least square. Step 1. Define the form of the curve. Choose a suitable mathematical model that represents relationship between the dependent and independent variables. Step 2. Define the object function. Typically, the object function is the sum of the square deviations between the observed data and the predicted values by the curve. Step 3. Minimize the objective function. This can be done analytically or numerically depending on the complexity of the mathematical model and the available computational resources. Linear regression, a simple example. Linear regression is a common application of curve fitting by the method of least squares. In linear regression, the curve is defined by a straight line, which is called as y is equals to mx plus b. The parameters to be estimated are the slope m and the intercept b of the line. Polynomial regression, handling nonlinear relationship. Polynomial regression is an extension of linear regression that can handle nonlinear relationships between variables. In polynomial regression, the curve is defined by a polynomial function such as y is equals to a plus bx plus cx square plus dx cube. The parameters to be estimated are the coefficients a, b, c, d of the polynomial. Nonlinear regression, modeling complex relationships. Nonlinear regressions allows for more flexible curve fitting by using nonlinear mathematical models. The curve can be defined by any nonlinear function such as exponential, logarithmic, or trigonometric functions. The parameters to be estimated depends on the specific nonlinear model chosen. Outfitting and underfitting, finding the right balance. Overfitting occurs when the fitted curve captures the noise or random functions in the data, leading to poor generation to new data. Underfitting occurs when the fitted curve is too simple and fails to capture the underlying patterns in the data. Finding the right balance between overfitting and underfitting is crucial for accurate curve fitting. Evaluating the fit, accessing goodness of fit. Several metrics can be used to access the goodness of fit, such as the coefficients of determination R squared, root mean square error, and Akaike information creation. R squared measures the proportion of the variance in the dependent variables that is explained by the fitted curve. RMSE measures the average deviation between the observed data and the predicted values by the fitted curve. Multivariate curve fitting, dealing with multiple variants. Multivariate curve fitting involves fitting a curve of data with multiple independent variables. The curve can be defined by a multivariate function such as y is equals to f of x1, x2, x3 and so on xn. The parameters to be estimated depends on the specific multivariate model chosen. Practical considerations, outliers and robust regress. Outliers are data points that significantly deviate from the general pattern of the data. Outliers can have a significant impact on the fitted curve and may need to be addressed. Robust regression techniques such as weighted least squares can be used to mitigate the influence of outliers. Applications of curve fitting by the method of least squares. Curve fitting by the method of least squares has a wide range of applications, including trend analysis, prediction, forecasting, and optimization. It is commonly used in fields such as finance for asset pricing models, in image processing for image reconstruction, and in physics for modeling physical phenomena. It is also utilized in machine learning algorithms such as support vector regression and neural networks. Advantages of curve fitting by the method of least squares. The method of least squares provide a systematic and mathematical approach to curve fitting. It allows for the estimation of curve parameters and the qualification of uncertainties through statistical inference. The method is widely supported by various software packages, making it accessible and easy to implement. Limitations and challenges of curve fitting. Curve fitting by the method of least squares assumes that the underlying relationship between variables can be represented by a specific mathematical model. The method can be sensitive to outliers and the noise in the data, which may require data pre-processing or outlier detection techniques. Complex nonlinear models may require advanced computational methods and longer computation time. Let's conclude that curve fitting by the method of least squares is a powerful technique for finding the best fitting curve that represents a set of data points. It allows for the estimation of curve parameters and the assessment of goodness of fit. The method finds applications in various fields and provide a valuable tool for understanding relationships in data. Thank you for watching my video. Do like, share and subscribe my channel. Thank you all.